So we're finishing up this coverage of this section on permutations and combinations with the binomial theorem, which tells us how we can expand a binomial raised to a power. This is, an algebraic operation we've done for a long time, back in algebra or pre-calculus. And this just sort of tells us the pattern of how we get those coefficients. So if I've got this binomial, meaning two terms, say a plus b, and I raise it to the nth power, when we expand it out, it's going to be the sum of a bunch of terms. And the way it works is you start with, R starts at 0 to n, that's our index. So we start with, say, all b's and no r's, all like b to the r power and then a to the 0 power, or b to the n power and a to the 0 power. And then those exponents on r kind of work their way up, and the exponents on b work their way down. And then we use a combination to figure out, to help us find that coefficient. I'm going to, before we do this example, just give a little context. We've seen this before. Think back to calculus, when you took calculus, and, one of the things we'd have to do when we did calculus is find the derivative by using the limit definition. Now, this combination stuff doesn't have much to do with the calculus, but we had to use this, and we did observe a pattern back when we learned about finding the derivatives of polynomials. So you might recall this being the limit definition of the derivative, and if you don't, that's okay. But it was when we had to find the derivative of something like, y equals x cubed, right? Or x to the fourth or x to the fifth, some integer, positive integer power on x. And in doing so, we'd have to find f of x plus h. So here, f of x plus h is x plus h all cubed, and we'd have to cube it out. If you took calculus with me, you definitely saw Pascal's triangle, and you may have seen it with other people, sometimes bring that out as well. But it was a shortcut for how we could expand this out without having to do too much distributing. So Pascal's triangle starts with a 1 at the top and a 1 and a 1, like a little triangle there of ones. Each row begins with a 1. Then we get the subsequent entries by adding these numbers together. And then each row ends with a 1. So our next row is 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And this could go on infinitely. So when we were expanding this out, we said, okay, look, I start with the pattern. I don't know what my coefficients are yet, but I got all x's, so x cubed, and no h. And then some unknown coefficient, step down that power on x by 1, so I have x squared, introduce a factor of h to the first. And then some unknown coefficient, x to the first, h squared. And then some unknown coefficient times h cubed. So we start with all x's, those powers go down by 1 each time. We start with no h's, but then those powers go up by 1. Note that as we go through, the sum of these exponents is always 3. And then the Pascal's triangle comes in because we were raising this to the third power, so I take the row that begins 1, 3, and I just throw down those coefficients. 1, 3, 3, 1. And there's there it is. This is related to the binomial theorem because, as it happens in Pascal's triangle, the entry in row I, column J, gives you I choose J. So we start, the top row is considered row 0. So like this entry right here, that's 1, 2, 3, row 3. 2 spaces in, so that's 3 choose 2, or sorry, 3 choose 1. So that's 3 choose 1. The first entry in each row is the 0th entry, 0, 1, 2, 3. So this is 3 choose 1, this is 3 choose 2, this is 3 choose 3. And so on. And that's what the binomial theorem tells us. So if we want to expand 2x plus 3y squared all to the fourth, what this tells me is that what this theorem tells me is how I can sort of put that together. So I'm going to start with r goes from 0 to n. So I'm going to have 4 choose 0. In this case, n is equal to 4 times a to the r, b to the n minus r. So my a is 2x and b is 3y squared. And it doesn't matter which one you call a and which one you call b as long as you're consistent. But this will be 2x to the 0, 3y squared to the 4th. My next term, 4 choose 1. 2x to the 1, 3y squared to the 3rd. 4 choose 2. 2x squared, 3y squared squared. 4 choose 3. 2x cubed times 3y squared to the 1st. 4 choose 4. 2x to the 4th. 3y squared to the 0. This is what the binomial theorem tells us. Now we just have some simplifying to do. There's a little bit of that to do. So 4 choose 0, that's 1. 2x to the 0 is 1. 3y squared to the 4th, that's 3 to the 4th. Y squared to the 4th. And we've got a bunch of algebra that we'll do. 4 choose 1 is 4 times 2x times 3 cubed y squared cubed. 4 choose 2 is 6 times 2 squared x squared times 3 squared y squared squared. 4 choose 3 is 4 times 2 cubed x cubed times 3y squared. 4 choose 4 is 1 times 2 to the 4th x to the 4th times, that's to the 0 power is 1. And then we just sort of clean this up. So 3 to the 4th is 81. Y squared to the 4th, multiply those exponents, y to the 8th. And let's see, then we have 8 times 27. It's 216. X, y to the 6. And we have 6 times 4 is 24 times 9 is 216 again. X squared y to the 4th plus 4 times 8 is 32 times 3 is 96. X cubed y squared plus 2 to the 4th is 16 x to the 4th. And there it is. So in this case, our binomial, right, the terms in our binomial had other coefficients, which also affected the overall, coefficients that we ended up with. The combination that appears in this formula just helps us find the overall coefficients. They won't be the absolute coefficients unless the coefficients on each of the terms inside is equal to 1. So we just have to be careful. A lot of the time that's not the case. And this works no matter how high the power is. Of course, you can see this was the 4th power. If the power gets much bigger, it can still feel a little bit unwieldy, although much more manageable than foiling everything out a million times. But sometimes, even if the power is very big, depending on what they're asking, it might still be a very manageable question to ask. For example, here we're looking at the expansion of 3x plus 4y to the 10th power. Right, so if I were to expand all that out, we could do it. It would just take a little bit. But they're not asking us to expand the whole thing out. They're simply asking us to find the coefficient of x to the 4th, y to the 6th. So in order to find that, to get an x to the 4th, y to the 6th term, that means that we must be picking the 3x 4 times, we need to pick that 3x term 4 times. And we need to pick the 4y term 6 times. So if we're looking for that coefficient, what we're going to do to find that term is just sort of going up and using this theorem. I'm just going to isolate that particular term where I'm picking 3x 4 times and 4y 6 times. So this theorem tells us that it will be 10 choose 4 times 3x to the 4th, 4y to the 6th. And we just need to find 10 choose 4. Let's see, 3 to the 4th, x to the 4th, 4 to the 6th, y to the 6th, 10 choose 4. Let's see, I can cancel that factor of 6 factorial and be left with 10, 9, 8, 7 up top. 3 to the 4th is 81. 4 to the 6th is 4096. 4 times 2 is 8. 3 goes into 9 3 times. So we have 30 times 7 is 210. And then we just multiply here. Okay, 69,672,960 x to the 4th y to the 6th. So that's the term. They said find the coefficient. So that means this is what we're looking for. That coefficient, very large. One thing I just want to draw your attention to, in both of these examples, the terms inside this binomial were both positive. If we, let's say we change this question just slightly, and they said, you know, find the coefficient in the expansion of 3x minus 4y to the 10th, we'd want to view that as 3x plus a negative 4y to the 10th, so that when we found the expansion, you know, we'd have to use a negative when we raised it to the power. And that when you were subtracting inside, you would see that it actually has sort of the effect of alternating the signs of the terms in the whole expansion.